Erin Massey. This is protein and amino acid metabolism or nutrition 701. Today, I'm going to be explaining protein synthesis. Specifically, we're going to talk about the translation part of protein synthesis. So at this stage, transcription has already happened, which is the DNA language then transcribing and turning itself into RNA. There are three types of RNA in the translation process: rRNA, mRNA, and tRNA. Mainly going to talk about mRNA and tRNA today. So what is tRNA, also known as transfer RNA, responsible for transferring the amino acid and the anticodon that matches with the mRNA, messenger mRNA. Anticodons and mRNA are going to be complements of each other. These three nucleotides make up what is called a codon. Those three nucleotides will complement the three nucleotides or codon that matches mRNA, and the amino acid is coded to also match the anti-codon and codon on the mRNA. So this is what a tRNA looks like. They're really, really small proteins. And tRNA kind of looks like a T, right? And the parts of it are really important. We've already explored the anticodon at the end. You have a 5' end and a 3' end that kind of wraps around. And there's a little cup on the end, which will carry a singular amino acid. It's also important to know these arms. The D arm is kind of your identification arm, and your T arm is your tethering arm, which is going to tether that tRNA to a ribosome. Ribosome is very important because it is the factory, the protein factory, if you will. So in making proteins, this whole process is happening in the juice of the cell, in the cytoplasm of the cell, actually at the cellular level. So you have tRNA, and there's mRNA. So this tRNA has to get here, but it has to be carrying an amino acid, because if it's not, it has nothing for the ribosome to use, right? So this amino acid has to be activated. Well, the tRNA has to be activated with an amino acid, but that process really needs to be helped. It doesn't happen all by itself. So how does activation happen? An enzyme is responsible for it, and we need to know the name of that enzyme. So a specific enzyme is going to bring this and this together. That enzyme kind of looks like a lobster claw. And in one section of the enzyme is going to be your amino acid, and the other section is going to be your tRNA with this little cup waiting for the amino acid. Important. To be able to make this happen, this enzyme needs energy. So this amino acid is actually going to have some ATP with it. ATP is never just ATP. To actually release that energy, you have to release a phosphate. And so it then becomes an amino acid and ADP. It's phosphorylated. The ADP amino acid tied together is known as the amino acyl synthetase. Synthetase. This is important. You have a tRNA and you have a synthetase. Combine those names, and what do you get? An amino acyl tRNA. synthetase. It's both of those things together, right? Can't spell. It's both of those things together. So you have your aminoacyl synthetase. So just amino acid with energy combined with your tRNA, and you have a synthetase, it's an enzyme, right? It's enzyming. And it's gonna clamp those things together. Now your tRNA is charged and you're ready to move on to the next step, which is matching the anticodon to your codon, but it's not that simple. So you have to have a ribosome to actually put those things together. So your protein making factory can't be forgotten. Also looks like a little spaceship if you look at that. And that's not that simple either, right? So you have your protein making factory. To actually start utilizing it, it has to be what's called dissociated. So dissociation is when the subunits of your ribosome, we'll call this 40S and 60S, measured that way for a reason. 40S and 60S are different subunits of the ribosome. They need to be associated, disconnected, separate parts to be able to actually initiate protein synthesis. And they can't do it on their own. They actually utilize something called an initiation factor, a eukaryotic initiation factor, to help this process out. They have helpers. So the initiation factor for 40S is actually going to be a 1, which gets the whole process going in itself. And because it's number 1, and initiation factor 3, which is specifically for 40S. 60S also has an initiation factor that helps them out. And it's going to be initiation factor 6, as in 60S. Probably not named that way on purpose, but that's how we're going to remember it. Okay, so that's step 1 of initiation. What is the second step? The second step is you're taking 40S and you're adding it to something called a ternary complex. Ternary. I know it's not tertiary, but ternary makes me think of 3. And there's things that need to be together for ternary complex to actually be created, which is kind of happening at the same time, just over here. Ternary complex, just call it TC for now, is made of a couple things. It's made of tRNA plus methionine, called methionine nil, which is kind of like your it's made of an initiation factor, another little helper. Initiation factor 2, actually, and 2B. And it's made of GTP as opposed to ATP. Very high energy. So for step 2 of initiation, along with the factors that are aiding in it, you combine tertiary complex with your top part of your spaceship, ribosome, 40S. That's part 2. These combine to make something called, and here's what we're thinking of it as tertiary, makes sense, helps you out, remember it, to make 43S. And it's also called pre-initiation complex. The 43, so you went from 40 to 43 initiation complex. This is kind of the second part, but we talked about the ternary complex. Continuing. The third one, you have this little, looks like an igloo now on here, but it's not really. You have you have 43, that's right, pre-initiation complex, and you need to combine it to your mRNA. And that combines to make 48 pre-initiation complex. 48. A little bit bigger, a little bit bigger, a little bit bigger stuff attached to it. So it's attached to your mRNA. And you're going to add the bottom part, which remember is 60S, which is a big subunit. And they combine with the help of another initiation factor called EIF5 to make 80S. So they're back together again, but this time they're on top of the mRNA, so they're combined. So now they're a happy little spaceship on its little assembly line, ready to make a nice, beautiful protein strand. So, with the help of initiation factors. So, going back, just to remember what initiation factors are involved real quickly, because we don't want to forget them. 1 and 3 go with 40S, so the top part of your ribosome. 6 goes with 60S, the bottom part of your ribosome. 2 and 2B go with your ternary complex, but 2B has a really important role, and that it's going to carry some additional GTP over when the ternary complex is being made, so that it has a little extra energy, so that it's a recharging unit, if you will. It needs another helper. And then there's initiation factor 5, which brings back your ribosomes together. It also, since those are together, there are a couple helpers that you don't need anymore. It gets rid of 3 and it gets rid of 1. It says, I'm done with you. Oh, sorry, 2 and 2. 1's still sticking around. So gets rid of 3 and 2. It says, we don't really need you guys anymore. Get out of here. I'm going to introduce some new initiation factors, which we actually didn't get to. So we got all the way over here to say, oh, it's combined with mRNA. 80S got put together with this initiation factor, number 5, but we skipped a number, didn't we? We went 1, 2, 3, 5, 6. Forgot to mention initiation factor 4, which there's multiple 4s, and they're very important in actually how this actually binds, how the ribosome actually binds to mRNA. So there is 4F, and 4F is composed of 3 things. It's composed of 4E, 4G, and 4A. And backwards, that spells age, makes it easy to remember. E is going to be responsible for clipping on the F prime end of the mRNA. G is, I like the word scaffolding, holding the A and the E onto itself. And A is then responsible for unwinding the helicase, the RNA helicase that's on top of the mRNA, which doesn't get mentioned until this part of the show. So it kind of, the helicase, so the mRNA kind of has this North Pole kind of look to it. It's not a perfect circle, I'm sorry. North Pole kind of look to it, and this is the helicase, and 4A is actually responsible for helping to unwind this so that the ribosome can attach the way it's supposed to. To further help you say that see that the G is scaffolding, G is going to be in the middle. Your E is going to be on the side, and your A is going to be on another side. And this is going to combine to this. And they're actually going to make a loop like a necklace. And there's one more initiation factor to know. Called initiation factor 4B. And 4B is just really going to help out 4A, helping it to unwind. So even the helpers have helpers. Kind of looks like a little present that's wrapped up, if you will, on the side, helping this to attach. But the idea is that one holds one end of the mRNA and the other holds the other so that it can do its thing. So you have this process, you have these helpers called initiation factors. And furthermore, these helpers, the initiation factors, are heavily regulated. So what does that mean? What does that mean, they're heavily regulated? Well, they're able to be turned on and off. I like to refer to this as the phosphorylation hokey pokey. So think about that song and get it stuck in your head the rest of the day. So you add a phosphorus, take away a phosphorus. You add one, you take it off, right? Takeaway after reviewing this over and over again is that there's really two initiation factors that are different from the others. And that is initiation factor 2 and initiation factor 2D. Why are these different? So if you recall, these are needed to make your ternary complex. These are needed to make the ternary complex. They are already equipped with these high energy molecules. And they require being phosphorylated to get to the next step. Well, if they already need to be phosphorylated as part of their natural process, and you add another phosphate to them, you're going to do the opposite. You're going to slow down protein synthesis when it comes to number 2. So 2B require energy, already have it attached to them. When you add phosphorylation to this, will decrease protein synthesis. Versus all of the other initiation factors enjoy getting that extra phosphorus and that extra energy. For dissociation to happen, it needs a phosphorus, that'll increase protein synthesis. See what else? So what else? The activation of mRNA requires energy, and that 4F, remember, 4F is going to bind and start that kind of ring effect, and it's going to start unwinding. It's going to form this necklace. That needs energy. That'll increase protein synthesis. Also, something interesting to know about the 4s when it comes to 4 initiation factors. There's age, right? Well, the E, which is the the first one to remember that's going to bind to that 5', actually has another helper, and it is called 4E binding protein, just number 1. And that binding protein is going to help it out. That needs energy to bind. That phosphorus, you increase protein synthesis. 4B is the last one that's helping A out. Add a phosphorus, increase protein synthesis. You increase all the others. So except for the 2s of the initiation factors, phosphorylation hokey is except for 2 is going to increase protein synthesis, right? So from a clinical perspective, looking at things that are going to increase phosphorylation, or Yes, increase phosphorylation, but stop protein synthesis, because what these have in common is they all work by affecting that initiation factor 2 and ternary complex. They all go back to the same thing, is when you have a deficit in amino acids, so you're starving. When you have a deficit of glucose, we'll go back to Y in a minute. When you have an infection or a virus, because your amino acids are being prioritized to make specific amino acids and specific proteins that are being used elsewhere in the body, you may have an indicator that says, stop using protein in our normal maintenance ways and start navigating, isolating those proteins towards the infection or towards the open sore or towards the virus in the body or in the bloodstream. That may happen then. There are actually sensors that can sense this. A few popular ones are going to be called GCN2. That's going to decrease protein synthesis by detecting low amino acids. In effect, that is eukaryotic initiation factor 2. And then the opposite, something called mTOR, it's quite famous. It's actually going to increase protein synthesis, unlike these things we talked about. mTOR is going to increase it because it can identify growth factors. So I might wonder, I know it's an animal, I wonder if that's affected in children who are growing or not. But those things are going to decrease protein synthesis, except for mTOR, so it's growth factors, or decrease versus not detecting it. We're going to go back to glucose. You don't have enough glucose can actually stop the process of protein synthesis. Talking about glucose, how does it do that? Well, if your glucose is low, you can still produce sugar and produce energy a couple of ways. The first way your body is going to do that is through glycogen. Your body can sense that your glucose is low. And it is going to produce something called glycogen synthase kinase 3. We're just going to call it K being sensed. It's going to increase this phosphorylation. And we already know that 2B does not like phosphorylation if we want it to produce proteins, if we want it to make that ternary complex correctly. So it's going to decrease that exchange of GTP to GDP. It's going to decrease that ternary complex. So that means no ternary complex. GDP exchange, which is going to decrease protein synthesis and decrease overall translation. So if you don't have glucose, which means your enzyme is saying, make more glycogen, stop synthesizing glycogen, you're not going to synthesize proteins. The opposite is true too. The opposite of this is true. If your glucose is high, glycogen's not being told to be released from the liver, then protein is abundant. Protein synthesis is abundant. So that is the second step in translation. You have a charged tRNA to deliver its amino acids, and then you have initiation with all of its initiation factors, bringing that ribosome protein making factory together. We'll talk about elongation next. Welcome back to protein synthesis. All right, so we've already had a charged tRNA, we've initiated it. This is on the mRNA. What's going to happen next? It's going to elongate. It's going to make the protein strand, the peptide bond, the peptide strand. How does that happen? It's important to know that the top part of the ribosome has 3 chambers. Spelled one way, EPA, and the other way, 8. It's kind of easy to remember which way that the strand is being weaved in this little factory based off of the letter. So A is arrival, P is your parking, so the little tRNA usually takes the route the longest, and then E is your exit, getting rid of it. So how is this process going to actually be helped along with more helpers, more factors, but these factors are not initiation factors, they are elongation factors. So there's two that we need to know. There's the elongation factor 1A and elongation factor 2. So 1A and 2. What does 1A do? 1A moves your tRNA, which again takes up residence right here, right? Anticodon, binding to your codon. It's going to start in here, but it's going to mainly put you guys in here. It moves the tRNA, comes into A, goes to T. That's what 1A is going to be doing, assisting in transport. And then EEF2, so elongation factor 2 is going to, oops, I got them reversed. We're gonna have to edit. So we have our initiation factors. 1A is going to be the binder for A. It's going to bind the elongation factor. It's going to bind the tRNA to the A site. And then F2, so EF2 is going to move that tRNA from A to P. So elongate, move it along, move it along, move it along. Until, if this is the top, you have this beautiful strand, and there's more enzymes that help with this. You have this beautiful strand of proteins coming along as tRNA moves along, right? So you get here, this is 20 some proteins, amino acids long. That's all it needs to be, right? That's all it needs to be. How do you terminate? So we talked about codons earlier, and there are 61 different codons that code for only 20 amino acids. That's where the wobble effect comes in and says, oh, well, you have an even less of a chance of finding the incorrect one because I'm going to pair the last code with multiple compared with iodine, right? So you paired correctly, let's assume, and you want to say, oh, we're done, cut it off. How do you cut it off? You have 3 stop codons on there. You have, I'll start with you. You are away. You are gone. And UGA, you go away. Like Georgia. No. So you have 3 stop codons. Once it senses that codon, which is going to be a tRNA without any charged amino acids, but an anticodon for your stop codon, you have 2 more helpers that come into play. You have ERF1 and ERF3. There's no 2 because that would make sense. So you have ERF1, and the R here stands for release factor. So initiation factors, elongation, and release factors. This is going to identify these stop codons. This is going to identify these stop codons. That's what ERF1 does. That says stop. And then the third one is going to cut the tRNA away from that peptide chain and said, okay, we're done. And that is protein synthesis. There's something you should know as far as regulation. I skipped. When you're making these proteins, remember your mRNA is kind of circular, right? Because of your 4F, your initiation factor 4F is holding it in a circle. Multiple ribosomes can be going along the circle at the same time, helping to make this strand. We call that polysome. That is if your glucose is sufficient and you're creating insulin to detect that insulin is sufficient. Multiple polysomes can be doing that at once, protein synthesis at once, making efficient proteins at an efficient rate. So that is initiation, elongation, and termination. Pause just a second, and I'll be back to talk about what happens next. All right, so what happens after translation is basically completed? Translation itself, to actually get those proteins made, is going to take 7 kilocalories per protein per gram of protein, or 25 to 30 calories per kilogram of body weight. That is the hospital calculation or oncology. So these are people with higher needs, normally ill. We talked about, viruses can sometimes obligate your proteins. So for maintenance and fighting off viruses, 25 to 30 is pretty high. That's usual. It's going to differ whether a person's obese, underweight. That's typically 15 to 20% of people's energy needs, right? So we know it took all this energy to make those proteins. Post-translation, those proteins are either going to stay in the cytoplasm, maybe they're going to become enzymes to become part of protein synthesis, or they're going to be sent to the ER, which it's not the emergency room, is the endoplasmic reticulum, which is part of the eukaryotic cell. And usually there's 3 reasons why it gets sent to the ER. It's going to be secreted. It's going to be part of the beautiful membrane proteins that make that semi-permeable layer, or it's going to become a lysosome or part of a lysosome. So the lysosomes are kind of your garbage disposal of your cell, right? So maybe that protein has an amino acid that wasn't meant to be there. Instead of having a mutation, this is the process that's going to stop cancer. That protein's just going to be degraded. It's going to degradation in that lysosome. It's going to be gone. So hopefully that doesn't happen to our lovely protein. Here is our peptide bond with these beautiful polysomes on it. So your ribosome, or your peptide bond that you just made, is going to have a tail on it called a signal sequence. That signal sequence helps it actually to become recognized by the endoplasmic reticulum. It has these things called it has receptors for what's called the SRP, which provide signal recognition particles. So it's going to be able to recognize the ribosome. And when it does, again, just like many of the organelles, the molecules, the ER is semi-permeable. So it's only going to let in the right protein that it's looking for. And it's going to open these gates after recognizing that little tail. And then it's going to pop off and go to where it needs to be. Most likely, it'll go to something called the Golgi apparatus, which is your post office of your cell. And then it'll send package those proteins and vesicles and send it wherever it needs to be inside or outside that cell.